Today's lesson is on polynomial functions of higher degree. So polynomial functions, if you remember, are in this form. So technically a quadratic and a cubic are a polynomial because they have a leading coefficient and a power or a degree. As long as this function has a beginning term, which means the first number is not 0, it's going to be a polynomial. Quadratics are polynomials of degrees 2, but cubic functions are a polynomial of degree 3, and quartics are polynomials of degree 4. Inside these polynomials, we have terms. Each term is separated by an addition or subtraction sign so that we make a sum of all of these terms, creating the entire polynomial. Standard form for a polynomial is when a polynomial is written in descending exponent order. I almost didn't fit it on there. Descending exponent order, meaning the very first term has the largest exponent and then it gets smaller from here on. Okay, they might not be written in standard form, but we have to remember that they should be written in standard form. We might have to rearrange them. Some more vocabulary just to clear out. Coefficients are the constants that are in front of all of the terms for the polynomial. The constant term is the very last term of the polynomial, so let's highlight that. The constant term is this very last term. And the leading term is going to be the very first term in the polynomial. So we start with the leading term and we end with the constant term. Notice the constant term doesn't have an x attached to it. Now there's a theorem that's really interesting about polynomials. It says that a polynomial function of degree n, so the largest power is the degree, has at most n minus 1 local extrema, so max and mins, and at most that number of zeros. So let's say we were thinking about a quadratic, that means it's a degree 2. That means it has at most 2 minus 1 or 1 extrema, and at most 2 zeros. Now that makes sense to us because if we think about a quadratic, the quadratic is going to have either a minimum or a maximum, 1 extrema. And it can have up to 2 zeros, but it really could have just 1 zero if it only crosses the x-axis one time. So this kind of makes sense to us. So if we think beyond just a quadratic, a cubic function can have at most 2 extrema pieces, 2 maxes or mins, and 3 zeros, just depending on the kind of function it is. But what's really important about knowing descending order or standard form of a polynomial is it allows us to immediately know about the end behavior of these polynomial functions. Now we're going to talk about end behavior in these limit statements. Now all of these limit statements are doing is talking about what's happening on the left side and the right side of the polynomial. So let's say we have an even degree polynomial, like a quadratic, and the leading coefficient is bigger than 0, so it has a positive leading coefficient. So a positive parabola or a positive quadratic looks something like this. Its end behavior would be that on the left side it goes to infinity, and on the right side it goes to infinity. So my end behavior as x approaches negative infinity, which if you remember is the left side, goes to infinity, and x as it approaches positive infinity on the right, also infinity. Now what's cool, and don't erase yours, I just want you to see, any even degreed polynomial, all that changes for it is what's happening on the inside. It can be squiggly wiggly like that. It could be just a regular parabola. It could be a quartic function. Doesn't matter as long as it is a even function or even degree, sorry, not even function, it's going to act like a quadratic at the endpoints. Now let's say this time though, we have the same even degree, but our leading coefficient is negative, like a sad parabola. So now my end behavior changes. I'm no longer going to positive infinity for both of these. They're both heading to negative infinity on the left and on the right. Remember that this term right here as x approaches negative infinity means left, and this means right. Again, it doesn't matter what happens in between here. This could be a whole squiggly wiggly line like this, but the end behavior would be the same as long as it is an even degree with a negative leading coefficient. If we think about an odd degreed function, the easiest odd degreed function to think about is just the plain linear. This is just x to the first power. This is what x to the first power looks like, where on the left side, we're going to negative infinity, and on the right side, we're going to positive infinity. So on the left side, we're going to negative infinity, and on the right side, we're going to positive infinity. That's the end behavior. Again, just like with the quadratic example, it does not matter if this ends up being cubic or if on the inside of it or whatever's happening is like crazy squiggly. At the end, it will begin to act like a linear function. So we can think of every odd degreed function as a linear in its end behavior. But let's say that leading coefficient is negative. That means it would be a negative sloped linear graph, so it's going to change to look like this, where on the left side, this time the arrow is going up to positive infinity, and on the right side, it's going to negative infinity. So we just change how we answer the end behavior. On the left side, we have positive infinity, and on the right side, we have negative infinity. That's how we talk about end behavior. Again, the different degrees are just going to change the insides of the graph, or where it's crossing the x-axis, kind of in the middle where I've been erasing, but the end behavior will always act the same, which means that the end behavior, or the limits at infinity, of a function simply depend on the degree of the polynomial and the leading coefficient. And I'm going to shorten that to coefficient. So the degree, whether it be even or odd, and then whether the leading coefficient is positive or negative. That's all that matters to tell the end behavior of a polynomial. What we're going to try to do here is, without a calculator, match the polynomial function with the 4 options down here. So match the graph to the equation. Now, again, we have a lot of different options here. We're looking mostly at the shape and at the end behavior. So let's first number these graphs 1 to 4, just so we know what we're working with. This is graph 1, graph 2, graph 3, and graph 4. For graph 1, its end behavior would be down on the left, so as x approaches negative infinity, it would be negative infinity, and positive infinity on the right. The second graph's end behavior would be positive infinity on the left, negative infinity on the right. The third graph would have the end behavior of negative infinity on the left and positive infinity on the right. And then graph number 4 would have the end behavior of positive infinity on the left and negative infinity on the right. Another thing we can notice about these graphs is how many zeros and how many pieces of extrema they have. For example, graph 1 has 3 zeros showing and has 2 extrema. What that means when a graph has 3 zeros and 2 extrema is that it can be a degree 3 or more polynomial, because it has 3 0 and 2 extrema. We had that theorem from the first page that says the degree tells you how many zeros it can have at most, and 1 less than that is the number of extrema. If we look at the second graph, we see that it has 1, 2, 3 zeros as well, and we have 1, 2, 3 extrema pieces showing. So again, that means we have at least 3 zeros and we have at least 3 extrema. That means from that theorem that this has to be a degree 4 or more, because it has to be 1 more degree than the number of extrema. It can be up to the number of zeros, but it has to be 1 more than the number of extrema. This one had 2 extrema, so 1 more would be 3 or more. With 3 extrema, through 3 maxes or mins, has to be 4 or more. We can do the same thing for graph 3. It has 3 coordinate points that are zeros, and 1, 2, 3 maxes and mins. So again, this degree can be 4 or more. And then the last one, we see visually that there are 1, 2, 3 zeros and 1, 2 extrema, which means that this could be degree 3 or more. That's again from that theorem from the first page. Okay, that's what we see in these graphs. Again, I've not graphed them. I don't know what their equations are, but we definitely can match up this end behavior and the degree for each of these polynomials listed A, B, C, or D. So for polynomial A, its degree is 3 because that is the largest exponent. We'd also say that its leading coefficient, the coefficient attached to that large exponent, is less than 0 because it's a negative number. Now, odd degrees functions that are negative, remember odd and negative is like a downhill slope for a linear equation. So no matter what happens in the middle, that's what our end behavior is going to look like. Which means that on the left side, the limit as x approaches negative infinity, our graph should be going to positive infinity. That's this arrow right there. Okay, and then as we go to the right, as x approaches positive infinity, that graph should be going downhill to negative infinity. So which one of the graphs, 1, 2, 3, or 4, has an end behavior that goes positive infinity, then negative infinity, and has a degree 3 polynomial? Yeah, this is going to be graph number 4. So without having to graph all of this crazy polynomial, f of x equal to negative 7x cubed plus 21x squared plus 91x minus 104, we know that it matches up to graph number 4. If we do the same thing for b, its degree, its largest exponent is 3, so it's also an odd polynomial, but the leading coefficient is greater than 0, which means that it's going to look like a regular positive linear graph with some different stuff happening in the middle. So its end behavior on the left is going to go to negative infinity, and its end behavior on the right is going to go to positive infinity. This is the left end behavior, this is the right end behavior. So down, up, left, right. Now, which graph has the end behavior of negative infinity to positive infinity and can be degree 3? That's graph number 1. That has the same end behavior and is the same degree. If we look at number C, letter C, sorry, it is a degree 5 polynomial, and that leading coefficient is negative, so its leading coefficient is less than 0. Odd and negative, again, is going to look like a negative linear equation, so downhill slope, with some different things happening in the middle. That first arrow goes to positive infinity, so the left side, limit as x approaches negative infinity, is positive infinity, and the limit as x approaches positive infinity is negative infinity. Is there a graph up there that can be degree 5 with that end behavior of positive infinity then negative infinity? Yeah, this is graph 2. Graph 2 has that correct end behavior of positive infinity on the left, negative infinity on the right, and it can be degree 4 or more. Well, 5 is more than 4, so that is the degree, that is the matchup for that polynomial. Now, very obviously, this is 3 because we have nothing left, but here's why. This is a degree 5 polynomial, and that leading coefficient is positive. So it's going to look something like a positive sloped line with some different stuff happening in the middle. But its end behavior goes from negative infinity to positive infinity. So we can match it up with what graph number 3 looks like. We were matching, again, the end behavior and the degree of the polynomial. We used the rest of this to decide the end behavior. And I know that that notation is new, so we're going to practice using just that notation for the problems on the bottom here. We're going to describe the end behavior using limits. Okay? Describe the end behavior using limits. To decide end behavior, like we said on the front, we just need the degree and the sign of the leading coefficient. The degree and leading coefficient for A, it's degree 3 with a leading coefficient that's positive. That's an odd positive graph, so it's going to look something like this, but not with that center. So we know that this is going to tell us the limit as x goes to the left, so that's x approaching negative infinity, of f of x is equal to whatever that first arrow was. And that first arrow went down, so that's negative infinity. On the other hand, the limit as x approaches positive infinity, which means I'm looking at the right side or the right arrow of f of x, is going to be equal to positive infinity because that arrow is going up. We have described the end behavior without having to graph it by just looking at the degree and the leading coefficient. I want you guys to try the next couple examples here. So go ahead and pause the video and see if you can write the limits for these graphs. Now hopefully this is what you wrote for those equations. For part B, it's an even positive. Even positive kind of looks like a quadratic, which means both arrows go up, so the end behavior on both the left and right go to positive infinity. Same thing for C, it's even and positive. And number D is odd and negative, which is like a downward sloped linear equation, which means on the left side it'd be going up, and on the right side it'd be going down. So we can talk about end behavior using those limits, which is just what's happening as you zoom way far out of the graph for all of these functions. Another skill that might be useful when it comes to polynomials is using their zeros, aka their solutions. Okay, zeros is just another word for solutions of a polynomial. I've written out 2 examples for you of finding zeros, which we've done before. When you're trying to find the zeros of a polynomial or the solutions of a polynomial, you just factor it and set each of the factors equal to 0 and solve. So x equal to 0, x minus 3 equal to 0, I would plus 3 on both sides, I'd get x equal to 3. And x plus 2 equal to 0, I would subtract 2 on both sides, get x equal to negative 2. Basically, it's the opposites. Same thing over here, we would factor out an x, use the difference of 2 squares pattern to continue to factor it completely until we have x equal to 0, x equal to 7, and x equal to negative 7. Okay, so we've found solutions before, and if you don't remember how to factor, that would be a great time to pause and maybe ask for some more help on that. But the reason that we find these zeros is to deal with multiplicity of zeros. Now, this is a new word for you, multiplicity. If f is a polynomial function and this factor, x minus c to some power m, is a factor of x, then c is a zero of multiplicity called m of f. Meaning that that zero has multiple zeros in that one factor. A zero of multiplicity that is greater than or equal to 2 is called a repeated root. Now that would sound familiar to you probably from before. If you end up having x equal to 2 as the solution twice for a polynomial, you would have called it a repeated root. And that's because it has a multiplicity or it'd be repeated twice. So here's what an example would look like of that. Here's a fully factored polynomial, but you have these powers beside each of the parentheses. Those are their multiplicities. So what I could do is I could quickly solve for the x values, setting it equal to 0. This would be x equal to 3, and this would be x equal to negative 2. However, the solution of 3 has a multiplicity of 3, and the solution of negative 2, has a multiplicity of 2 because of these powers here. That's its multiplicity. That's how many times that particular solution is repeated in that polynomial. It's a repeated root. Again, it's just the same number that is the power. What's great about these multiplicities is that it allows us to be able to graph these functions knowing what happens at each of those zeros. So if a polynomial function f has a real zero of odd multiplicity, so the number that is floating on the outside of the parentheses is an odd number, 1, 3, 5, 7, you get it. Then the graph crosses the x-axis at that particular number, at that 0, and the value of f changes sign there. So really the main thing you need to know is at that 0, it crosses. But if the polynomial function has a real zero of even multiplicity, meaning it's 2 or 4 or 6, then the graph does not cross. In fact, it doesn't cross so much that it just bounces, and that's what we're going to write down, bounces off of the axis at that point. It does not change signs. It does not cross. So for example, in this graph right here, okay, we're graphing x plus 2, x minus 1. The multiplicity of both of these is 1. So that means at the zeros of -2 and 2, which I would find, I would have zeros there, and for both of those, this polynomial would cross through there. It would cross through at both zeros. But because on the second example, that x minus 2 has a multiplicity of 2, that means when I graph that solution of 2, my parabola cannot cross the x-axis there, so it stops and it bounces right back up. That's called a repeated root, or having an even multiplicity. So odd crosses, even bounces back. Odd crosses, even bounces back. Now what I've done here, because it's a time saver, is I've gone ahead and showed you a full example of how you would use all of the information we've done today to graph a function. So we start by stating the degree and the end behavior, finding the zeros, talking about their multiplicities, and then whether the graph crosses or bounces, then finding the y-intercept so we can graph this function. Here is the whole example from start to finish. We are graphing this function without a graphing calculator. I know that it has a degree 5 because I took these multiplicities, 3 and 2, and I added them together. That's how many times I would have solutions. So it's an odd and positive polynomial. It's positive because if I were to multiply all of these out, I'm multiplying positive numbers times positive numbers to get my leading coefficient, so it's never going to be negative there because these are all positive numbers, the first ones. So that means it's going to have the end behavior that looks like a positive linear graph because it's odd and positive, meaning on the left side we're going to go down to negative infinity, and on the right side we're going to go up to infinity. Since it's already factored, I can take each of these factors and set them equal to 0 and solve. This would give me x equal to -2, and this would give me x equal to 1. Now the multiplicity of -2 is 3, and since that's an odd number, we know we're going to be able to cross the x-axis at that point. So let's go ahead and write that in as something extra here. So at -2, we're going to be able to cross the axis. These are just notes for ourselves here. At the other 0, x equal to 1, it has a multiplicity of 2, which means it's not going to cross. So underneath that one, we're going to write the word bounce. Because we cannot cross over that coordinate point, we're just going to bounce off of it. Now the last thing I did was find the y-intercept, which if you think back to when we did piecewise functions, we found the y-intercept by plugging in 0. I don't have to choose where to plug it in. I plug it in for all of the x's. This would be 0 plus 2 cubed and 0 minus 1 squared. Well, 0 plus 2 is 2. 2 cubed is 8. 0 minus 1 is -1. -1 squared is 1. So my y-intercept is 8. What I've done on this graph is I have graphed everything, every piece of information I've talked about so far. All I have to do is correctly connect the dots. I start at this very first end behavior on the left, going to negative infinity. All right, I'm going to put my pencil there. And I'm going to go to the first 0. Now that first 0 says cross, which means I can cross over that 0 to the other side. I'm going to go hit my y-intercept because that's another coordinate point. Then I'm going to come aim down for the next 0. But that next 0 says bounce. So instead of crossing over, I'm going to bounce right back off and go try to meet up with my next coordinate point or end behavior. So what this does is it allows us to write really good sketches of these graphs, just plain connect the dots not only with the zeros, but also with the end behavior. Let me graph that again one more time so you can watch it, okay? So I started at the left end behavior, which was to negative infinity, and I go to the first 0 or the first important coordinate point. It says cross because that's an odd multiplicity, so I keep going. I catch my y-intercept. I'm going to come back down to my next 0, which is the next important point. It says bounce because it's an even multiplicity. So I bounce off of that and then go connect the dot, which whatever I have left, which in this case was another end behavior. Now would be a good point. If that made no sense to you, flag me down, ask me some questions, because the next thing you're going to do is try it on your own. You've got a blank graph here with sort of a typo. Pretend like this floor isn't floating too high up. That is the multiplicity of this particular factor. Please go ahead and try sketching this graph. You've got all of the steps there for you. I'm going to pause the video and then show you what it should look like. Okay, here's some of the information you should have. We know, because this is a degree 6 polynomial and positive, that its end behaviors both go to infinity. So we can have that already pre-graphed on my graph, that the end behavior, the arrows, would go off to infinity. We then found the zeros, and we know that for both of them, because they're even multiplicity, they're going to bounce off of those zeros. So I'm going to go ahead and make that note for myself so I remember to not cross there, but to bounce. Then I have my y-intercept. Okay, so I have all the pieces to play connect the dots. I would have started at the left end behavior, come down to the first 0, bounce, go up to the y-intercept, come to the next 0, and it says bounce again because it's even multiplicity, and meet up at my end behavior. So that's a pretty accurate sketch of what this graph is going to look like. Now, this idea of crossing or bouncing through the axis is really helped by what's called the intermediate value theorem. The intermediate value theorem says that if f is a continuous function on the closed interval from a to b, and f of a is not equal to f of b, and k is any number between f of a and f of b, then there is at least one number c in a comma b such that f of c equal to k. And you're probably thinking, Miss Quigley, that was a whole bunch of math that makes no sense. You're right, it's very confusing, but it makes a lot of sense. Here's what it means. If this is going to be A, and this is going to be the letter B, we're looking at the interval in between them. Well, every function has an input and an output. So let's say that our graph looks something like this. Okay, we have some inputs at f of A, and it goes to f of B. Okay, that's our graph. This would be A, and this would be B and f of B. Right? That's how coordinates work. Inputs, outputs. We are saying they are not equal to each other. Okay, they're at different levels. And we're going to pick some number in between them. We're going to call it k. Then we're saying then there must be some number here on the number line for the x-axis such that these also line up. This is a very duh thing. Here's what it means in real life. When I woke up this morning and took my dog for a walk, I wake up at 5 a.m. So at 5 a.m. it was 64 degrees outside. Legit, I looked at my watch this morning. I also looked at my watch at exactly 3:39 p.m. and my watch said that it was 92 degrees Fahrenheit. So question for you. If this is my input, my A value, and my output, this is my B input and my B output, my question for you, at some point today, has it been 70 degrees Fahrenheit? Obviously, to go from 64 degrees to 92 degrees on this continuous function that is temperature, we did have to reach 70 degrees to get from 64 to 92. That's what the intermediate value theorem is telling me. At some point, from 64 to 92, we had to cross 70 degrees. That's helpful when we're graphing these functions. This idea of being able to graph the zeros comes from this intermediate value theorem. At some point today, was it 85 degrees Fahrenheit? Yes, because 85 is between 64 and 92. So obviously, yes. But at some point today, was it 94 degrees Fahrenheit? Since this number is outside of the range that we're confident about, the 2 times I took the temperature, we have no idea. it could have been at some point, but we cannot prove it with the intermediate value theorem because we are not sure if it ever actually reached that. We only have information about what happened at 5 a.m. and 3:39 p.m. All of the values that we know need to be in between those. So again, this is why we're able to graph those functions with those zeros. There are 3 things you have to prove for this function to show it. Number 1, you need to show that it's a continuous function. It's either going to state it's continuous or you have to state it's continuous. The second thing is you have to show that f of a does not equal f of b and that k is between f of a and f of b. Then we're able to prove the final part of this or state the final part of this, that there's at least one number c in that interval such that f of c is equal to k. This is kind of like a writing question, so stick with me on the writing. In example 4, here's how it might look. We want to show that f of x equal to 0 has at least one solution in the interval between -2 and 2 for this function, f of x equal to x cubed minus x. The first thing we do is show that it's continuous. So we say f of x equal to x cubed minus x is continuous on the interval that they stated, -2 to 2, and why? And we're going to say because it is a cubic function. We know cubic functions from our study of the 12 basic functions are continuous on their entire domain. The second thing we have to prove is that the inputs, or the outputs, at both of the ends of this interval are not the same. So we would actually need to evaluate what f of -2 is, which means I'm going to be plugging in -2 to this equation. -2 cubed is equal to -8 minus -2, that's +2, so that's going to be equal to -6. F of 2 is 2 cubed, I wrote a whole square, I'll make that a cubed, minus 2, that's 8 minus 2, which is +6. So we can see that these two numbers are not the same. So the goal of this question, remember, was to prove or show that 0 had to show up at some point on that interval. Well, isn't 0 in between the numbers -6 and 6 on a number line? Like, I'd have to pass 0 to get from -6 to 6. So we're able to say that the f of -2, which was -6, is less than 0, which is less than f of 2. We're essentially saying that this output we want has to appear between those two numbers that I've highlighted, -6 and 6. So we write our final statement here. We've proved the two things we needed, so we say, therefore, there exists a c value in the interval from -2 to 2 such that f of c is equal to 0 due to the intermediate value theorem. So we just wrote basically a whole math essay to answer this question. We proved, again, step 1 is to show that it's continuous, and sometimes you just have to state it. This is a cubic function, so it's continuous. We know that about cubic functions. We plugged in the first interval and the second interval, found that they were not the same number, and that 0 shows up between them. So we said this statement. This is very important right here. Once we have both of those statements, that it's continuous and the one I just underlined, we can say the math sentence, therefore, there is a number, some number c, in the interval from -2 to 2 such that if I plugged that number in, I'd get 0, which is what I want, due to this intermediate value theorem. Okay, here's where this sort of question would come in real life. Now, this is a very AP calculus question. This is how it's asked, and it might have this like free response style question, but it's all to do with the intermediate value theorem. A car travels on a straight track, and during the time interval from 0 to 60 seconds, which is seen on the graph, 0 to 60, the car's velocity measured in feet per second is a continuous function. Ding, 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 we need that. That's our step 1. The table below shows the selected values of the velocity. Our question here is, for between 0 and 60, for time from 0 to 60, right? Must there be a time t when the velocity of t is equal to -5? Then we're going to justify our answer. So this is the number we're looking for to be in our outputs. Okay, let's start looking for that number on this table. Well, first things first, I don't see the number -5 on this table. But I know that -5 would show up like about here, somewhere in between 35 and 50. Because it would be in between -10 and 0. So to justify saying yes, we say the following. Number 1, v of t is continuous. We literally just have to state that because it's part of the intermediate value theorem. But they told us that in the question, so that's enough information. The second part was to show that f of the first interval, 35, is equal to -10. I got that straight out the table. 35, -10. And that f of 50 is equal to 0. Therefore, because -5 is between -10 and 0, we can say that f of 35 is less than -5, which is less than f of 50. Remember, this is the number we are looking for, and this is just -10 and 0. And -10 is less than -5, which is less than 0. We have both things stated, so we can do our conclusion. Therefore, there exists a number t in the interval that they stated from 0 to 60 such that the v of t would be equal to -5 due to the intermediate value theorem, which you can shorten to IVT. So again, we showed that it was continuous, which they gave us in the example. You have to just state it again. And we noticed that -5 would show up between these two numbers. So we used these inputs and these outputs in my explanation and justification. Therefore, there exists some time t in this entire interval, 0 to 60, such that v of t is equal to -5 due to the intermediate value theorem.